Welcome to this special edition of Frequency Matters. I'm Pat Hindle, and I'm here with Dr. Eric Bryerton, and he's a senior engineer at Virginia Diodes. You guys are involved in a very interesting project with NASA to do ice cloud mapping, and you use a 833 gigahertz radiometer that you supplied. Can you tell us a little bit about that project and how you got involved?
Yeah, definitely. Thanks for having me. So actually I was, before starting at Virginia Diodes, I was at the National Radio Astronomy Observatory for several years. And I was actually first contacted about this project when I was there by the technical lead at Goddard Space Flight Center for this project, Dr. Nagar Hassan. We shared the same PhD advisor, so she knew me, and she knew I'd worked on millimeter wave power amps. So she contacted me for the amp. She contacted VDI for the multiplier chain, and that was when they were writing this proposal. And then a year or two later, when this proposal was accepted, I had since moved to VDI. So now sort of everything, all the technology that was needed was in one place, and the proposal was accepted. So we got together and took a visit to Goddard, and then the order was placed, and then a year later we had the thing built.
So this goes on a CubeSat, appropriately named Icecube in this case. Can you tell us a little bit about the science that it does?
Yeah. So at the spectrum around 880 gigahertz, where this is centered, is one of the most sensitive areas to sensitive parts of the spectrum to the size of ice particles and ice clouds. So if you were to plot the brightness temperature or the system temperature that you're looking at versus particle size, you get the steepest slope right around 880 gigahertz, 870 gigahertz. So you have the most sensitivity there, and that's important because the distribution and the composition of ice clouds in the atmosphere is one of the critical parameters going into climate models, into making climate models more accurate. But of course, then the trade-off at 880 gigahertz, of course, is your receivers are much more difficult to build, tend to have higher noise temperatures. So this is kind of a proof of concept to see if 880 gigahertz, 870 gigahertz really is kind of the sweet spot for doing these measurements.
And so you have some of the components here. Can you tell us, what type of circuitry and devices go into making up this product?
Yeah, certainly. So this is a mock-up of the Icecube science plate. So it was a 3U CubeSat, where each U is a 10 by 10 by 10 centimeter volume, and the actual front end, the receiver part, the millimeter wave part, needed to fit on this 9 by 9 centimeter plate and take up about 2.5 centimeters height. So there's a few kind of critical technologies, challenges in something like this. So it's a heterodyne system, and a heterodyne receiver at nearly a terahertz is a huge consumer of DC power, because you have to generate a local oscillator up near a terahertz with a few milliwatts coming out of it to drive the Schottky mixer. So to do that, you would traditionally start at a low microwave frequency, 12 or 15 gigahertz from a DRO in this case, and then amplify it, multiply it, amplify it a lot, and then go through successive stages of multipliers, each one with just a few percent efficiency. So one of the developments that VDI had from actually a previous SBIR contract with NASA was to develop a set of very high efficiency varactor multipliers targeted specifically to these critical atmospheric windows. So we had these high efficiency varactors which lowered the overall DC power that you needed to start with. So that was kind of the critical technology one. Number two is having the highest possible frequency power amp, so that because your power amp is generally going to be more efficient than your conversion efficiency of your multiplier. So having this new, and this is not VDI technology. This has been developed for military applications and for new comm applications such as 5G. Having these amplifiers in the E-band range with 100, 200 milliwatts of power with pretty good power added efficiency. So starting with that and then going to these high efficiency varactors at sub-millimeter waves allowed us to have this Schottky receiver with just a few watts of DC power. And then the third thing is having the ability to integrate things into a very small volume. So you eliminate all the flanges in between each component. So for example, there's basically two parts on here. The DRO is at 15 gigahertz, and that's a COTS product, and that's going to be over here. And that goes into this. This is a ×3 active tripler, and there's a mimic power amp at 70 gigahertz on the output. There's a flange here and it's connected to this block, which contains both a varactor doubler, a varactor tripler to 440 gigahertz, and then a second harmonic Schottky mixer at 880 gigahertz. And then there's a horn going out here. And on the real deal, there's an ellipsoidal mirror here, so that you're looking out this way, is coming in, bounces off this mirror, goes into this horn antenna, and the IF goes off here, off to the back end processing. So those three things, having the high efficiency varactors, the millimeter wave power amps, and then kind of the compact integration, allows this all to happen.
Well, that's a lot to put into the system. Was there any other design challenges based on the space flight requirements?
Yeah, that's a good question. Yeah, so there was advantages in being a CubeSat versus a traditional flagship kind of space project. So there wasn't as many restrictions on using space flight qualified parts. You could use COTS parts, and that's basically what we are. We are a COTS supplier to NASA for this. And it also means that we don't have to use space qualified parts in our modules. We could do things a lot quicker, which we're used to doing. Some of the challenges in going to space, even on a small platform like this, is you don't have in the CubeSat, you don't have the power to really to give you good temperature control. So this had to be able to work reasonably well over a wide temperature variation as this thing's going around in orbit, and sometimes in the sun, sometimes not in the sun. So we had to do quite a bit of testing over a fairly wide temperature range to see how it worked. And that was probably the most significant difference for us.
So I think you were one of the early COTS CubeSat projects and programs. How do you see this benefiting the science going forward?
Good question. So, yeah, it's kind of so this particular project is, like I said, a proof of concept that you could do these measurements at 880 gigahertz, and that it is very sensitive there. And the eventual idea is to have more of a constellation of these types of CubeSats, so that you can map more efficiently, the whole surface of the Earth. Another example would be another project we're working on is with a different group, is to develop a suite of receivers to go on a small constellation of CubeSats for measuring the evolution of tropical storms. So this measures water vapor in the atmosphere over the tropical regions, and instead of sort of flying over with a huge satellite the same area of the tropics every 6 hours, with a constellation you can fly over. You'll hit the same part of the Earth every 20 to 30 minutes. So you'll get a new update on the storm track every half an hour rather than every 6 hours, which you can imagine could save lots of aggravation in terms of evacuations, and could potentially save billions of dollars in sort of hardening your infrastructure in the right places. And actually, this was the Icecube CubeSat, and this is a prototype of this one I was just talking about, which is kind of shows, I don't know how much you can see, but there's quite a bit integrated into just a single receiver. It's got the entire radiometer, 4 channels, many filters, several LNAs at 180 gigahertz, several Schottky detectors. So again, it's a challenge of just putting everything in as small a package and as low power as possible, so that you can fit onto these small volumes.
Well, we really appreciate you talking to us today on Frequency Matters and doing a lot of interesting science here at Virginia Diodes, and thank you for watching.